All right, I'm going to be talking about multi-threaded programs and testing them with KLEE. And there we go. Basically, I'm not going to give you the whole spiel about how multi-threaded CPUs are more and more important. I'm sure you've heard this all before. But the thing is, symbolic execution and KLEE especially usually considers serial programs, right? This is not the first work that considers itself with parallel programs. However, we, at least I would claim, made a bit of an improvement. But this talk today is not about the theoretical ideas that we use to make that work, but it is about how we actually build that for KLEE. Adding support for multi-threaded programs to KLEE sounds kind of simple, right? I mean, well, you just need to have multiple stacks in a state. Then maybe you need a concurrency-aware searcher so that you don't get stuck. And of course, you need some kind of API that you work with. pthread is the big one when you're doing concurrency, but it doesn't have to be, right? Now, of course, if that was that simple, I wouldn't be standing here and wouldn't be giving this talk. So let's see where it breaks down. In the beginning, if you try that, it'll go all swimmingly, because you can easily extend KLEE states to track multiple stacks and instruction pointers, right? I mean, it's not that hard. But once you try to do anything with that, you will end up with an immediate state explosion. And when I say immediate, I mean immediate in the sense of single-digit instruction immediate, not in the sense of immediate as in the first hour. That is because the number of possible paths to a concurrent program is, a bit simplified, is the number of threads raised to the power of the number of instructions per thread. Now, to give you a tiny example, let's assume I have an 8-core machine and I want to execute 20 instructions per thread. That's not a lot. However, that also already means 2 to the 60 paths through that tiny little concurrent program. And that already means we can't even enumerate it, not even talking about actually storing it in memory. And in general, even if you don't, want to explore everything, maybe still executing any single instruction turns that one state that we just executed instruction into number thread states, right? Exponential growth, we're kind of used to. However, we're used to it being, at a branch, maybe we get, in the worst case, 2 states out of it. Not like we're having here suddenly that at every single instruction, we suddenly have a dozen options. In general, we figured that any approach that tries to, deal with the state explosion after the fact is not good enough. That doesn't mean that they don't have their place, and that doesn't mean that they can't help. However, we need to start earlier in our general approach and then go ahead from there. Now, to show the problem and a bit of our solution, let's consider this horribly complicated program where we have 2 threads, and each thread does the work of performing 1 increment. In thread 1, we incremented global A. In thread B, we incremented global B. So don't be surprised. This is a standard load increment store. but there is nothing hidden in here, right? I've chosen LLVM for this, LLVM IR for this presentation here, but could have been anything, of course, right? Now, at this point, these two threads, they don't interact with one another, and there is no need to interleave them in any way because they don't touch anything that is the same. When we make this a bit more complicated by adding another increment, this time to a shared variable, there start to show up cases where we want to interleave different concurrent behavior to show what might happen. Now, when we're incrementing x, there actually turns out to be 4 different paths through this, depending on the loads and the stores. Now, you might be forgiven thinking that I'm about to explain to you how to deal with the loads and stores, maybe dive into weak memory models. In fact, however, we want to do the exact opposite. We just want to point out that data races are undefined behavior in C. Now, since that just means that, assuming we are executing C programs or any program really that follows the C memory model, of course, there is no question about how to interleave these instructions, because trying to do that is plain wrong, as in bug wrong. And this is basically how we deal with this, right? Our KLEE fork detects data races as a new bug category, which of course is nice already, but not the end all be all. But to do that, we just record which thread read or wrote any single byte the last time. And if we find a mismatch, a data race, we can just abort it. This is kind of efficient if a memory object is used by one thread exclusively, as is the case for the vast majority of memory objects. And most memory objects are not shared between threads. Symbolic accesses to shared memory objects may still require SMT solving. So if we do have kind of the worst case, we have a memory object that has symbolic indices, for example, into a shared array between different threads, that is actually kind of expensive. However, that's not really what we're usually seeing. Going back to the example, what does that mean for us? Well, basically, this is a bug, right? This program like this, we're done. We don't need to do anything concurrent. Every concurrent path that we have is a bug. So of course, we can be very fancy programmers and add a bunch of lock and unlocks, basically putting a critical section around the increment here. Note that this is also what happens when you do an atomic increment. We just basically lower this to a non-atomic but locked increment. Now, of course, this is not a bug anymore, but more importantly, there are now only 2 options left. We can do the critical section on the left-hand right first, or the critical section of thread 2 first. There are no further options anymore. This is a vast reduction in the number of possibilities compared to both the raw and also the case where we do interleavings at every instruction, and also the case where we do interleavings based on any kind of weak or strong memory model directly on the binary level. In fact, we only need to consider 4 scheduling points because we still need to consider 4 scheduling points because, of course, this is a simple pattern. And in general, it doesn't have to be a simple critical section pattern. It could be any arbitrary combination of arbitrary pthready calls, right? So you could have 3 calls to lock followed by an unlock, a condition variable wait, and another unlock. Now, of course, the big thing in here that I'm not talking about is the partial auto reduction that we're using to then make that even more efficient. However, we end up realizing that if two paths yield the exact same state, we only need to pursue one further, a concept that you may know from state merging, right? This happens all the time in parallel program. It's comparatively rare in serial programs, but for example, the program that we just saw has two states that in the end are the same thing. We detect such cutoff events by hashing all the memory, which of course fails if there's even a 1-bit difference. Also, our partial order reduction algorithm re-executes some states. These re-executions must yield the exact same state as the original execution, because otherwise, again, we're not re-executing the same state, but doing something different. And this yields to something, to a result that we found out to be really very important, and that is that the symbolic engine, or KLEE in our case, of course, needs to be as deterministic as is humanly possible. There are, of course, cases where we know this is impossible, external function calls, but in general, we need determinism. So to conclude, our KLEE fork can symbolically execute multi-threaded programs. We have support for most POSIX threading primitives, including condition variables. And the whole thing relies on recognizing data races as bugs. For the validity of our partial order reduction, and of course, because we want to have the performance. And then finally, it requires deterministic re-execution of states, which took us a long time to get to work reasonable, because it really demands a lot of KLEE in the determinism department. For those of you who are into concurrency, we combined symbolic execution with a quasi-optimal partial order reduction to deal with the data non-determinism from the KLEE side, with basically just ordinary KLEE, and of course, using the partial order reduction to deal with thread interleavings. You're welcome to check out our tool. It's open source and a KLEE fork. And if you're interested in how the actual algorithms work, you're welcome to read the extended version of our CAF20 paper. The extended version has a lot more detail on the algorithms, possibly more than you really wanted to know. Thank you.